Welcome to the second video in a series of 4 on logarithm and exponential functions. In this video, we'll look at combining and expanding logarithmic expressions. Let's look at combining first. Suppose we were given this algebraic expression. Now, each of these logarithms, you might imagine, is a decimal, which could be figured out on a calculator. Log base 5 of 4 means that power of 5, which equals 4. That's obviously not going to work out to a whole number, nor is the second one, the log base 5 of 7. Well, this logarithm is also a decimal. And it turns out that the two decimals on the left add up to exactly the decimal on the right, which brings us to an interesting rule. See if you can see the connection between the expression on the left and the expression on the right. I'll pause while you think. If your brain caught on to the fact that 4 times 7 is 28, you've discovered an interesting rule about logarithms, that you can add two logarithms together, as long as they have the same base, which they do in this case of 5, that you can add two logarithms together by multiplying the arguments. We call this the sum property for logarithms, and it can be expressed symbolically like this. Sometimes, for visual clarity, we don't write the base b. You may remember if you saw video 1 that I had mentioned if a logarithm ever has a blank base or no base written, that it's assumed to be 10. This is the one time where that's not the assumption. Here we're simply stating that two logarithms of any base when added together equal the logarithm of the product of the arguments. We're not implying that this is only true for base 10, but it's a much nicer looking formula without the bases written. Here's a second expression. Of course, each of these is a decimal as well. Log base 9 of 20 means that power of 9, which equals 20. Well, that's clearly a decimal, as is the second term here. But this is also a decimal, and it turns out that when you subtract the two decimals on the left, you get the decimal on the right. I'm going to pause for a second and see if you can see where the 4 came from. If you thought it came from 20 divided by 5, you're right, which brings up an interesting rule, which essentially we call the difference property, which states that you can subtract two logarithms, as long as the base is the same, by dividing the first argument by the second one. Symbolically, in general terms, we could write it this way. And again, for visual clarity only, let's erase the b's. And you can see the general idea here. One logarithm minus another is the log of the quotient of the two arguments. Here's a third expression. Notice this is a whole number times a logarithm. And it turns out that, of course, that logarithm is a decimal. And if we were to multiply that decimal by 3, we would get the same decimal as we get for this logarithm. I'm going to pause for a minute and see if you can figure out where the 125 came from. It takes a clever person to see this. It turns out it came from 5 to the third power. We call this the coefficient or scalar property, which essentially says if you have a non-logarithm times a logarithm, notice the expression on the left side of your screen, a non-logarithm times a logarithm, you could rewrite it by raising the argument to the power of the coefficient, or in this case 5 raised to the third power is 125. In more general terms, we could state that formula this way. And again, just for keeping things simple, we can erase the b's to give a more clear picture of what the scalar property is. So let's take a look at a situation. Suppose I were given this expression here, the sum of two logarithms. Couldn't I use the sum rule that we just developed? Since the bases match and they're both 7, I could simply multiply the arguments a times y and get log base 7 of a times y. That seems pretty much in line with what we just saw called the sum rule. But in reverse, if I were given this expression, the logarithm of a product, notice this says the log base 7 of a times y, or the times is implied anyways. Couldn't I then expand that into a sum of logarithms? In other words, it raises an interesting question. Which one of these two things is the math problem, and which one of them is the answer? Well, it turns out it depends on the directions. If you're given a problem and you're told to express it as a single logarithm and you have two or more logarithms, then you have to find a way using the previous rules to combine those, and then that would be the answer. Reversely, if you were given the expression on the right as your problem and told to express it as a sum or difference without exponents, sometimes we say expand it, sometimes we just say to write it as a sum or difference and we don't mention the exponents, but whatever we say, if we're giving the impression that here's a single logarithm and we'd like you to expand it in some way, then that would be the answer. So it's better not to think of these as math problems or answers in and of themselves. It's better to think of them as two equal expressions, either one of which could be converted into the other, depending on the directions. Here's a problem. Suppose we were told to express this as a single logarithm. Well, right now it's two logarithms. By the way, side note, the fact that these are natural logarithms, ln, as opposed to other logarithms, log, doesn't make any of the rules any different. Both of these logarithms have a base of e, you'll recall, if you saw the first video, and so therefore there's some combinability in this expression. Let's move on with the problem. The first thing I'd like you to notice is that we have a times and a subtract in this problem. And as we always do in algebra, multiplication comes before subtraction. Also, it's worth noting that that multiplication sign won't always be visible. So when you see a number sitting in front of a logarithm, always interpret it as the number times that logarithm. So we're going to do our multiplication first. Well, for this, we're going to use the scalar or the coefficient rule that we just saw, which allows me to take x to the third power. And now that I've done the multiplication, let's do the subtraction. Well, how do we subtract logarithms? We use the difference rule by taking the quotient 4 over x cubed as the argument of our new logarithm. So what have we done here? We've taken an expression with two logarithms, and we've used the order of operations along with the logarithm rules to condense or combine this into a single logarithm. But what if the answer to this problem were the problem itself under a different set of directions? That could reversely just as well be the case. So you might be given this expression and asked to express it as a sum or difference without exponents. Well, first of all, notice that this problem, which is the answer to the previous problem, notice that this new problem is the logarithm of a quotient. And according to the difference rule, we can split that up into a subtraction of two logarithms. And that would be a fine answer if it just said expand. But since it specifically said without exponents, then I can't have an exponent on my x. I can't have my cubed there. So I'll use the scalar rule in the reverse as you saw me use it before, this time in essence bringing the 3 down as a coefficient. And now the answer to this problem was the problem itself in the previous situation. Of course, all of this raises an interesting question. Why do we combine logarithms sometimes and expand the logarithms other times? Well, the answer to that lies in higher mathematics courses. typically calculus or higher. There are situations in which we're better off for the purposes of the problem we're in to have more than one logarithm. And there are other situations where the problem would be done easier if we had a single logarithm. Unfortunately, if this is your first or second time learning about logarithms and this is relatively new to you, you sort of have to just do this blindly and follow the directions without any regard for what actual purpose it serves to separate logarithms sometimes and to condense or combine them others. But it does serve a purpose later on. Now we're just practicing the act of expanding or combining depending on the directions. Let's take a look at another. Suppose we were trying to express this as a single logarithm. I have a recommendation. I'm going to recommend that you pause the video, try this problem yourself, and then hit play. Go ahead and hit pause now. Okay, here's what I did. First, I noticed that there were two multiplications in the problem. Looking at the top line, there's a 3 times a logarithm and an 8 times a logarithm. So I did my multiplication first by using the scalar or coefficient rule. Now, I have a subtraction and an addition. As far as the order of operations goes, we work those out left to right. So since subtraction comes first, I'll do the subtraction next. So I'm subtracting the log base 4 of x cubed minus the log base 4 of y to the 8th. Those can be combined into a single logarithm using the difference rule. And finally, I'll do my addition. Again, since the bases match, I'm allowed to combine these two logarithms or add them together by multiplying the arguments. So I'm going to multiply x cubed over y to the 8th times z. And of course, that gives me this new argument and my final answer per the directions of expressing as a single logarithm. So here's some uncommon situations, but things that you should be aware of nonetheless. Suppose we had logarithm minus logarithm, as in this expression here. Couldn't I, according to the difference rule, just turn this into a single logarithm, 500 over 5y being my new argument? Of course, that's the difference rule. Couldn't I also then simplify? After all, 500 is divisible by 5, and because the denominator is a product 5 times y, that allows me to simplify to the logarithm of 100 over y. Pretty reasonable based on all the rules that you've seen so far. And in fact, if the directions to this problem had been to express as a single logarithm, then I've done exactly that, haven't I? I've taken two logarithms and condensed and then simplified them into one single logarithm. Great, problem's done. But here's an uncommon situation to ponder. What if instead of those directions, I had been asked something different? To express as a sum of an integer and a logarithm. Side note, reminding you that an integer is any whole number or the negative of a whole number. So not fractions or decimals, basically. Okay, so right now I don't have this expressed with an integer at all. I have two logarithms, neither of which is an integer because, for example, the logarithm of 500 we saw earlier is some decimal that's about 2 point something. Well, I could still use the same rules to express it as a single logarithm, but then couldn't I, if I wanted to, because I have the log of a fraction, couldn't I expand that back out into a subtraction problem using the reverse of the difference rule? Well, of course I could, but it begs the question, why would I want to condense something into a single logarithm and then expand it back out? Well, ordinarily, I'm not sure that I would, but based on the directions here, I think it was a smart choice. Follow me on this strange train of thought. The log of 100. Notice there's no base underneath the g in logarithm. No base means that the base is 10. This is a common logarithm. So this first term on the left in green is saying that power of 10, which is 100. Can you think of a power of 10 that's 100? Of course you can. It's 2. And now what I've managed to do by compressing, expanding, and then resimplifying this expression, I've got it to match the directions. I've expressed it as a sum of an integer and a logarithm, 2 being the integer, log of y being the logarithm. Now this is an uncommon situation, and it makes most students very uncomfortable because there's no predictable way to necessarily arrive at the answer. When you're given the directions to express as a sum of an integer and a logarithm, you simply have to use your algebraic creativity, toying around with the rules of expanding and compressing until you get the expression that matches the directions you were given. In most mathematics courses, it's unlikely that you'll be asked to do something like this, but it is worth knowing that logarithms, in terms of their simplification and rewriting, are not just things that have clear-cut problems and answers. Logarithmic expressions are things that can be manipulated to our particular desires of the situation. By the way, a final note about this problem, you'll notice the subtraction in this answer, or so-called answer here, really means I've expressed it as a difference, haven't I? Sometimes when we say to express something as a sum, we're generically including in a bigger umbrella the notion of expressing it as a difference or a sum, just so you know. Strange problem. Here's another one, another uncommon situation. Now I'm being asked to express this as a single logarithm. Okay, well right now it's the sum of an integer and a logarithm, not just a single logarithm. And so I've got to somehow combine these. Remember the sum property from earlier in this video? That sum property doesn't apply to this situation, does it? Because we don't have a logarithm plus a logarithm here. We have a non-logarithm plus a logarithm. What's the rule for a non-logarithm plus a logarithm? Well, there is no rule. So there appears on first glance to be nothing that I can do here. But here's a clever thought I had. You see this 2 here on the left in green? What if I rewrote 2 in a different way? Wouldn't it be nice if I had logarithm plus logarithm here to make it combinable by the sum rule? So what if I rewrote 2 as the log base 3 of 9? And that seems like a really strange thing to do. I mean, how often in math do we complicate the problem? Well, sometimes we have to complicate the problem before we simplify it. Now, if you're a little confused, follow me on this side journey. Suppose you're taking a test, and the test problem asked you to simplify the log base 3 of 9. That would mean that power of 3, which equals 9. Okay. Well, isn't that 2? Well, if that's the case, can't I reverse that logic? Look at the left of your screen and notice that I've changed 2 into the log base 3 of 9. It's that element of creativity that we sometimes need in math to continue. Now again, begs the question, why would I want to complicate the problem? Well, because now, by complicating the appearance of the problem, I now have logarithm plus logarithm with the same base, mind you. And so I can then use the sum rule to combine those logarithms together by multiplying the arguments 9 times y and getting 9y, thereby completing this problem. It's tricky, but something to be aware of. So we're essentially done with all of the logarithm work that I wanted to cover in here, but before we end the video, let's take a minute to talk about parentheses and functions and how they relate to how we write logarithms. Take this expression, for example. This means that power of 4, which equals 7. I hope it's sort of clear to you by now that there's no multiplication sign here. We're not multiplying a logarithm by 7. Logarithms are a function, log base 4 a particular function, and this is log base 4 of 7. not log base 4 times 7. That wouldn't even mean anything. And so with that in mind, if it's a function, shouldn't it then have parentheses, like most functions do? Well, technically, yes. But sometimes, for simplicity of viewing, or just writing, we leave the parentheses off the logarithm. Compare these two expressions that you see at the top of your screen. I think both of them are obviously interpreted as that power of 4, which equals 7. That, by the way, works out to be approximately 1.4. But I don't think anyone would interpret one of these differently than the other. The moral of the story being, there are times when there is no danger in leaving the parentheses off the logarithmic function. By contrast, consider this example. Now, as we discussed, there's no multiplication here, but there is a multiplication here. And that raises an interesting question. Did the author of this expression mean it for the argument to be 8, or did they mean for the argument to be 8x? And without parentheses, we simply don't know. If they meant the argument to be 8, then they meant this. By the way, log base 5 of 8 works out to be about 1.292. And so if the author's intent was that the argument was 8, then that would be the expression, 1.292x equivalently. But on the other hand, if the author of this expression at the top of your screen meant for the argument to be 8x, then this is what they meant. But wouldn't that be equivalent to this, using the sum rule? And substituting a decimal value, just to prove a point here, in for log base 5 of 8, which I got from my calculator, that would be a much different expression than if the argument were just 8, as implied by the left side of the screen. Of course, then the question becomes, well, what did the author intend? And we don't know. I often will write log base 5 of 8x without parentheses with the intention that 8x is the entire argument. But every author is different. Every writer of mathematical expressions is different. So please, when communicating your work to professors or anyone else, please be careful to use parentheses around logarithm arguments when there's any danger of misinterpretation. And that completes our second of 4 videos.